So today's video is on ozone, the formation and depletion. So first we're going to look at breaking bonds. So another word for breaking bonds is just bond fission. And there are two types of bond fission, which is heterolytic fission and homolytic fission. So heterolytic fission is the one we're going to start looking at. So this is when both the electrons in a covalent bond go to one of the atoms. So if this is our covalent bond, we have our two bonding electrons, and during heterolytic fission, both of these bonding electrons in the covalent bond go to the chlorine. So they go to one of the atoms in the bond. And so this forms our negative and positive ion. So heterolytic fission forms a negative and positive ion because both of the bonding electrons go to one of the atoms. So heterolytic fission is common in polar bonds, and this is when one atom is already more electronegative than the other, and electronegative means it attracts the bonding electrons more. So this has a higher electron density around it. So this chlorine is already more electronegative. It attracts these bonding electrons more. So the electrons will be around this chlorine more often, meaning it's more likely to take both of these electrons with it during heterolytic fission. Now, homolytic fission. Homolytic fission is when one electron in the covalent bond goes to each of the atoms. So if this is our covalent molecule, we have our two bonding electrons, and during homolytic fission, one of the bonding electrons goes to each of the atoms in our covalent bond. And this forms two radicals, and radicals are species with an unpaired electron, and these are very highly reactive and usually react with anything they touch. So homolytic fission is common in non-polar bonds, and this is because if they were more attracted to one atom than the other, then it would be more likely for heterolytic fission to happen. It would be more likely that one atom would take both of the bonding electrons and it would form ions. But with non-polar bonds, it's more likely that the atoms will be shared between the two, the electrons will be shared between the two atoms. However, homolytic fission can happen in polar bonds, and this is usually when they're in the gaseous phase or they're in the presence of light. So this is photodissociation, so the breaking of bonds due to photons due to light. So now looking at the formation of ozone. So in the troposphere, it's photochemical reactions. So photochemical reactions in the troposphere, so this is closer down to Earth. So photochemical reactions with primary pollutants. So these are directly emitted from a source. So this is stuff like carbon dioxide. And this leads to ozone formation. And these photochemical reactions with primary pollutants also leads to other secondary pollutants being created. And this all contributes to photochemical smog. And ozone is a pollutant in the troposphere. But in the stratosphere, ozone is formed by photodissociation of dioxygen molecules, and we'll be having a closer look at that later. So ozone as a sunscreen. So when ozone is hit by UV radiation from the sun, it absorbs this UV radiation. So the sun emits this high energy UV that could be very damaging to our Earth, and ozone in our stratosphere absorbs this high energy UV. And it uses this UV to break down ozone into dioxygen and oxygen again. So you can see here that this is our formation of ozone, our dioxygen plus our oxygen atom to get our ozone. But when our ozone is hit with this high energy UV, it reverts back into the reactants. So this reaction is actually a reversible reaction, meaning the formation and depletion naturally occur at a similar rate. So our oxygen is forming our ozone due to these photochemical reactions under the presence of light, and our ozone is being depleted at the same rate by absorbing this UV radiation. And it's this absorbing of UV radiation and using it to break down its own molecule that's responsible for radiation screening, because this high energy UV doesn't reach the Earth because it's being used for the ozone to break back down into its reactants. So now looking at ozone depletion in a closer look. So when we break down ozone in the stratosphere, it now cannot screen the Earth from high energy UV. So before it was absorbing the high energy UV, breaking down into its reactants, but these reactants could reform to form our ozone again to continue screening from this radiation. But when we break down too much ozone at a time, it means that there's not enough ozone in our stratosphere to screen us from this high energy UV radiation. And this is very bad because it can damage bonds in our DNA. And this means that it can lead to skin cancer. It can also damage proteins in the skin, so this high energy UV can damage these proteins, which can cause our skin to go leathery. So when we are in the sun too much, you can notice that sometimes we age a little quicker with our skin, and this is because it damages the proteins, causing us to go have leathery skin premature to the age where we would naturally start developing it. And this high energy UV can also irritate blood vessels to appear red and sunburnt. So this is when out in the sun we come back sunburnt because this high energy UV irritates our blood vessels. So now we're going to be looking closer at what depletes ozone. So we have our general equation at the side here, and in the next slide we'll be going over that step by step. But first we have to notice that there is X, and X could be chlorine, bromine, nitrogen oxide, hydroxyls, for example, and these are all radicals. So this radical is our reactant in our first reaction, so we have to know that it will be these molecules, these radicals, that will cause this ozone depletion. And out of these radicals, chlorine is the most abundant in our stratosphere, so we're most worried about chlorine depleting our ozone. However, bromine is 100 times more effective at depleting ozone than chlorine. However, it's not in a massive concentration compared to chlorine, so we're not as worried about it. It's chlorine that is very abundant in our stratosphere at the moment, which is worrying us about this ozone depletion. And you can see that these radicals are catalysts. And this is because they are removed unchanged from the reaction. So you can see here that we have our radical, and it's produced unchemically changed in the products as well. So it is a catalyst for ozone depletion, meaning after the reaction, after it has depleted this ozone, it can go on to deplete more ozone, which is why it is so dangerous for our stratosphere. It's because it has a long residence life. It can continue this chain reaction to deplete more ozone. So now we're going to look at the process of ozone depletion using our general formula. So we can see that in our first reaction, a radical, which could be any of the radicals we saw in the previous slide, our radical reacts with ozone in the stratosphere. So in the stratosphere, our radical reacts with our ozone molecule, and a new radical is created. And radicals are species with an unpaired electron. And radicals are very reactive. They react upon collision with pretty much anything. So our new radical that we've created, along with our new dioxygen molecule, so we've taken a oxygen from our ozone and it's reacted with our radical to form this new radical, and we've got a dioxygen molecule out as well. So our now very reactive new radical can go on to react with a single oxygen atom. So this oxygen atom may have been formed by the reaction of ozone depleting into dioxygen molecule and a oxygen as it absorbs UV. So the reaction we saw in the previous slides, the reversible reaction between ozone and its reactants. This could be one of those oxygen atoms, and it now, instead of going on to react with another dioxygen molecule to reform our ozone, it's instead going to react with our new radical. And so then we get out the same radical we started with. So we get back this radical that we had in our initial reaction, and we get it out here. And then we also get another dioxygen molecule. So this is really important because both of these radicals that we have created are intermediate radicals, so they're present in both the products and the reactants. So this means that to get an overall equation, we can take them out of the equation. So our overall process of ozone depletion is ozone that we get from the first reaction, plus an oxygen atom that we get from the second reaction, plus two dioxygen molecules that we get in the products of both reactions. So you can see here that we've got a radical reacting with our ozone. It forms a new radical plus a dioxygen molecule, and this new radical can now go to react with an oxygen atom, which forms our original radical and another dioxygen molecule. And it's getting back out this initial radical, this catalyst, that allows this radical to go on to deplete more ozone, to continue this chain reaction, which makes ozone depletion such a dangerous thing.